Why mass creates gravity? This is a question so simple that most textbooks do not even ask it. They tell you that mass curves space-time. They give you the equation, they move on, but they never answer the one question that matters. Why? And I know this because I am the one who wrote the equation. My name is Albert Einstein, and I am about to explain something to you that your textbook got wrong. Let me start with a confession. When I first proposed general relativity, I did not have a complete answer to this question either. I had the mathematics, I had the geometry, but the mechanism, that remained hidden, and it has remained hidden for over 100 years. But we are finally, slowly, beginning to see the shape of the answer, and it is stranger than anyone imagined. Most people think gravity is a force. They imagine an invisible hand reaching out across empty space, pulling things together. This picture comes from Newton. Newton gave us a formula, beautiful and clean, that works for almost everything we need on this planet. But Newton himself knew something that most textbooks conveniently forget. He wrote that the idea of action at a distance, this invisible hand reaching across nothing, was so absurd that no man with a competent faculty for thinking could ever believe it. He gave us the formula because it worked, but he admitted freely that he had no idea what was actually happening. He called it a great absurdity. 2.5 centuries later, I had what I later called the happiest thought of my life. It came to me in 1907 while I was working at the patent office in Bern. I was thinking about a man falling from a roof, and I realized something so simple that it seems almost trivial. A man falling freely does not feel his own weight. He is weightless. Now, put that man in a sealed box. He cannot see outside. From inside that box, there is no experiment he can perform that will tell him whether he is falling in a gravitational field or floating in empty space far from any star. The two situations are identical from his perspective. Now flip it. Accelerate that box upward at 9.8 meters per second squared. The man inside feels a force pushing him into the floor. He cannot tell whether he is standing on the surface of Earth or accelerating through empty space at that precise rate. Gravity and acceleration are locally equivalent, not similar, not analogous. In the precise technical sense, they are the same thing seen from different perspectives. This is the equivalence principle, and from it everything follows. If gravity and acceleration are equivalent, then anything acceleration does to light, gravity must also do. So what does acceleration do to light? It bends it. Fire a beam of light across your accelerating box. By the time the light reaches the far wall, the box has moved upward, so the light hits the wall lower than it started. From inside the box, the light appears to have curved downward. By the equivalence principle, gravity must do the same thing. Gravity bends light. I predicted this in 1915. 4 years later, Arthur Eddington measured the deflection of starlight passing near the sun during a solar eclipse. The light bent exactly as I had predicted. The world changed overnight. But that spectacular result, the one that made me famous, is not the deepest thing that general relativity tells us. The deepest thing is this: gravity is not a force at all. It is geometry. Mass and energy curve space-time. Not space alone, but the four-dimensional fabric in which every event in the universe takes place. And what we experience as a force pulling us toward the Earth is actually the geometry of that curved space-time. We move in straight lines through curved space-time, and those straight lines, called geodesics, look from the outside like curved trajectories in flat space. The orbit of the Earth around the Sun is the Earth traveling in the straightest possible line through the curved space-time created by the sun's mass. There is no invisible hand. There is geometry. This is what the textbooks tell you, and it is correct as far as it goes. But it leaves the deepest question unanswered. Why does mass curve space-time? What is the physical mechanism? What is actually happening at the fundamental level when a concentration of energy bends the shape of the universe around it? I have to be honest with you about something. The equations of general relativity describe the curvature of space-time with extraordinary precision. They tell you how much curvature a given distribution of mass and energy produces. They tell you how objects move through that curved space-time. They have passed every experimental test we have ever thrown at them, from the precession of Mercury's orbit to gravitational waves from colliding black holes detected 1 billion light-years away. The equations work, but they do not tell you why. What is the physical process by which the presence of mass causes space-time to curve? What is actually happening at the most fundamental level? And before you say the answer is gravitons, quantum particles of gravity, let me stop you. Yes, that is the expected answer. Yes, that is what quantum field theorists have been working toward for 70 years. And yes, we do not have a working theory of quantum gravity, not because smart people have not been working on it, because it is genuinely, spectacularly hard. Every naive attempt to quantize gravity, the same way we quantize electromagnetism, runs into mathematical problems that currently have no satisfactory solution. But here is where it gets interesting. In 1974, Stephen Hawking made a calculation that terrified everyone, including himself. He showed that black holes are not entirely black. They radiate not a lot. For an astrophysical black hole, the temperature is fantastically close to absolute zero. But they radiate, they emit thermal radiation purely because of quantum mechanical effects near the event horizon. And in doing so, they slowly lose mass. They evaporate. The calculation was a tour de force. Nobody doubted it. But the problem, the terrifying problem, was what it implied. If a black hole evaporates completely, what happens to the information about everything that fell into it? You throw a book into a black hole. The book contains information, the arrangement of atoms, the words on the pages, the quantum state of every particle. The black hole evaporates. What Hawking's calculation suggested was that the information was gone, destroyed, radiated away as featureless thermal radiation that carried no information about what had fallen in. Hawking believed this for years. He defended it. He was very smart and very stubborn, and he was wrong about this particular thing. I thought he was wrong because it violated a principle I consider sacred, unitarity. The principle that quantum mechanics preserves information that you can always, in principle, run the movie backward. Hawking thought this principle could be violated by black holes. We argued about this for 2 decades in lecture halls and papers and conferences. These were real arguments, not performances. We both believed we were right about something fundamental. The resolution came from an unexpected direction. It came from the holographic principle, the idea that the information content of a region of space is not proportional to its volume, but to its surface area. The boundary of a region of space-time contains all the information about what is inside it. Like a hologram, where a 2-dimensional surface encodes a 3-dimensional image, this is not a metaphor. This is a mathematical result. In 1997, Juan Maldacena discovered something remarkable. He showed that a theory of gravity in a certain kind of space-time, called anti-de Sitter space, is mathematically equivalent to a quantum field theory without gravity living on the boundary of that space-time. Exactly equivalent. Not an approximation, not an analogy, a precise mathematical duality. This means that in this framework, gravity is what you get when you look at a certain kind of quantum entanglement from a particular perspective. The curvature of space-time, the thing we call gravity, is encoded in, and in some sense generated by, quantum information on a boundary. Let me make this concrete. In 2006, Shinsei Ryu and Tadashi Takayanagi discovered a formula that says something remarkable. The entanglement entropy between two regions of the boundary theory, a purely quantum mechanical quantity, a measure of how entangled the quantum states in those regions are, is equal to the area of a minimal surface in the bulk spacetime that connects those regions, divided by 4 times Newton's constant. In other words, entanglement on the boundary equals geometry in the bulk. The shape of spacetime, the thing that gravity is literally written in the pattern of quantum entanglement. Think about what this means for the question we started with. Why does mass curve space-time? Because the presence of mass changes the pattern of entanglement. Matter is, in some fundamental sense, a way that the quantum degrees of freedom of the boundary reorganize their entanglement. And this reorganization, when viewed from the bulk, appears as a curvature of geometry. I want to be precise about something. We do not have a complete theory of this for our actual universe. Our universe is not anti-de Sitter space. The correspondence applies exactly to a toy universe with different properties from the one we live in. The extension to our universe, the universe with a cosmological constant that seems to be accelerating its expansion, is an open problem, and not a small open problem. It is one of the central open problems in all of theoretical physics. But the clue is too big to ignore. If space-time can emerge from quantum information in one context, that tells you something profound about what space-time actually is. It tells you that the question, why does mass curve space-time, is at the deepest level a question about quantum information and entanglement. So where does this leave us? Your textbook told you that mass curves space-time and that gravity is geometry. That is true as far as it goes. But it is incomplete. It describes what happens without explaining why. The deeper answer, the one we are still working toward, is that gravity may be an emergent phenomenon. It may arise from something more fundamental, something that lives on boundaries, something that is purely quantum mechanical and informational in nature. Mass creates gravity because mass is a concentration of energy, and energy is information structured in a particular way. And the structuring of information in that way produces, through the quantum mechanical relationships between the degrees of freedom of space-time, the phenomenon we call curvature. Gravity is not a force. It is not even fundamentally geometry. It may be the shape that information takes when it becomes entangled. The textbooks will catch up eventually. They always do. But for now, when someone tells you that mass curves space-time and leaves it at that, you can ask them the question they are not asking. Why? And you will know that the answer, when we finally have it, will be stranger and more beautiful than any of them ever imagined.